4.7 is optimization. This is the last section that we cover technically in Chapter 4. 4.9 moves on to Chapter 5. So optimization allows us to figure out the best case scenario in any given situation. It uses the first derivative in order to figure out a maximum or a minimum for a scenario. Okay, so there's 4 steps in this process. Step 1, you want to define your variables and develop an equation. Step 2, you want to determine the interval and the critical points. Step 3, you want to optimize, which means derive and analyze those points. And step 4 is write a conclusion. Okay, so we're going to start with a simple example here, example 1 from the textbook, and then I'm going to jump around in these notes for the video and just do a couple of key problems, and then once we're in class we'll go through more of them together. Okay, so a piece of wire, length L, is bent into the shape of a rectangle. Which dimensions produce the rectangle of maximum area? So sometimes diagrams are given to us and fully labeled, and sometimes the word problem would be more informative and we would have to come up with these diagrams. All right, so step 1, defining the variables, developing an equation. So what are we looking to maximize? We're looking to maximize area of a rectangle. So that's the equation that we're coming up with. Area equals length times width, x times y, however you want to write that. Okay. And then based on how the variables are defined in the problem, then we would replace in our equation. So area is equal to x times L over 2 minus x. We always want to simplify the equation that we're going to derive before actually deriving it. So here I can avoid my product rule. 1/2 Lx minus x squared. Now, remember that L is a constant, so it looks as if we have 2 variables here, but L is just some constant, and that's what we're trying to kind of figure out. And therefore, when we're deriving 1/2 Lx minus x squared, it's not implicit differentiation. We're just deriving with respect to a single variable. So A prime ends up being 1/2 L minus 2x. We set that equal to 0 and we solve, and therefore x is equal to 1/4 L. So we want to look at the endpoints and the critical points. So in terms of our endpoints, sometimes going back to the diagram is helpful, right? X, of course, has to be greater than or equal to 0, as well as L over 2 minus x has to be greater than or equal to 0. That's really the only information we have here. Based on that, if I manipulate this, my interval goes from 0 in terms of x to 1/2 L, right? Because x then becomes less than or equal to L over 2. Okay. So we have 1/4 L, we have 0, and we have L over 2 to analyze. We always take those and we put it back into the original equation to determine which one will yield the largest area, the maximum area. So if x is 0, then we just get 0 for our area. If x is 1/4 L, then we are going to get 1/16 L squared. Right, I'm plugging it into right here. And if x is 1/2 L, we end up with 0 as well. Most of the time in this section, you guys, the critical point is what's going to maximize the scenario. So 1/16 L squared is the largest area that we can come up with, and our dimensions would be 1/4 L by 1/4 L. Okay. All right, so I'm going to jump to the third page in your packet, and we're going to look at number 43 here. Okay, so Brandon is on one side of a river that is 50 meters wide and wants to reach a point 200 meters downstream on the opposite side as quickly as possible by swimming diagonally across the river and then running the rest of the way. Find the best route if Brandon can swim at 1.5 meters per second and run at 4 meters per second. Okay, so we've got to define our variables and come up with that equation. So in order to do that, we have to draw a picture. So I'm going to put Brandon right here. Okay, and there's a river that is 50 meters wide. Okay, and Brandon wants to make it downstream to a point here. But he's going to do so by swimming some diagonal and running the rest of the way. The total distance downstream that he wants to make is 200. So if I make this part of the triangle x and the rest of the way 200 minus x, then we can come up with the distance that Brandon swims by using Pythagorean theorem. So if this were c, then 50 squared plus x squared equals c squared, and c is equal to the square root of that. Okay. Now, more information is given. We know how fast he can swim and how fast he can run. And the question, again, we always want to go back to what is the question. Find the best route. And if we're trying to come up with the best route, and they're talking about time a lot, we want to minimize our time, right? We want to minimize this, not the distance necessarily, but how long does it take to get from point A to point B. So then we want to think about our equation of distance equals rate times time and manipulate it so that it says time equals distance divided by rate. Right? So that's what we're looking to minimize in this situation. Now, Brandon is doing two different things. Therefore, we will have two different ratios of distance over rate based on his swimming and his running ratio. So he's going to swim a distance of square root 50 squared plus x squared, and that is at 1.5 meters per second. And then he's going to run a distance of 200 minus x, and that is at a speed of 4 meters per second. So we have two ratios separated with addition. Okay. Now, we want to clean this up a little bit. We want to write it in a way that will be much easier to derive. So remember that the division of 1.5 and the division of 4, they're really just coefficients. They're just fractional coefficients. So I'm going to write it like that. That's the only step I'm going to take when I am simplifying this. Okay. Okay. So when I derive with respect to x, I have a chain rule in the first term. So I would have a 1/2 times a 1 over 1.5. So I have a 1 over 3. 50 squared plus x squared to the negative 1/2. And then times the inner prime of 2x. Okay. And the second term, right, if I were to distribute here, it's just a linear. So the only term that will continue to come through is a negative 1/4. So now what I'm going to do is rewrite things so that I can solve it a little bit easier, right? My whole job now is to set it equal to 0 to find my critical points. So in my numerator, I have a 2x, and in my denominator, I have a 3 square root 50 squared plus x squared. minus a fourth. Okay. So now I can start moving things around so that I can come up with what my x solutions are going to be. So I'm going to create a ratio, a proportion, adding 1/4, and that equals 2x divided by 3 square root of 50 squared plus x squared. I can cross multiply, and I would have 3 square root 50 squared plus x squared equals 8x. If I divided by 3, and then I squared, that would bring me to 50 squared plus x squared is equal to 7.113x squared. Of course, this is a calculator active question. I wouldn't expect all this without a calculator. And then keep solving, right? I don't have a b term, so I don't have to worry about quadratic formula or factoring. I can just combine like terms. I have 2500 equals 6.113x squared. Divide by your 6 and take the square root, and x comes out to be 20.23 meters. So that's our critical point. Now, the other values, the interval that we would come up with, the domain restriction, well, x could be 0, right? Because Brandon could swim directly across the river horizontally. Or x could be 200, where Brandon swims all the way to the point. So we have 3 points to test. We have to test t of 0, t of 20.23, and t of 200. We put those into our original time equation, and we want to look for the shortest amount of time that it takes Brandon to complete this. So if I plug in 0, I'm going to end with 83.3, and this is seconds. If I plug in 20.23, I'll end with 80.9 seconds. If I plug in 200, I have 137.4 seconds. So the optimal scenario for Brandon completing this is 80.9 seconds, and that is if he swims at a diagonal that is 20.23 meters downstream and then runs the rest of the way. Okay. So we're going to look at just 2 more questions here, and they are on the last page, questions 4 and 5. These are the style questions that are most common in the AP, which is why I want to make sure I show these in the video, and then we'll go through the other questions in class. So number 4 is really common, and it doesn't even necessarily appear as an optimization because it's not so much of a word problem, but it is optimization. We want to find the point P on the curve y equals root x that is closest to the point 3, 0. So first thing, I'm going to sketch the graph of square root of x, which appears like this. I'm going to put the point 3, 0 on my x-axis, and I'm just going to throw this ordered pair of x comma y here. Right? We are trying to minimize this distance right here, which means we are trying to minimize our distance formula. Distance formula is x2 minus x1 squared plus y2 minus y1 squared, and square root of all of that. Okay, so the one thing that you have to do here, so far it's not so difficult, but if I were to write my distance formula exactly as I see it, I would do x minus 3 squared plus y minus 0 squared. Now the issue I have here is now I do have an equation that has 2 variables in it, and I can't have that. I need to replace one of the variables with respect to the other. And I do it by using the relationship that y is equal to root x. So that ordered pair of x comma y that I wrote is really the same as writing x comma root x. Okay, so before I derive this, I'm going to clean it up. I'm going to FOIL things and combine like terms and then derive it. Okay. So I have the square root of x squared minus 5x plus 9 to derive, so much easier to work with. D prime is then chain rule 1/2 inside to the negative 1/2 times inside prime. There's a couple of different explanations for why this portion of it will not yield the answer. Some have to do with just reasonability, some have to do with linearity, some have to do with just pure logic, right? We're going to get an answer, a very nice, simple answer, when we take 2x minus 5 and set it equal to 0, and that answer is 2.5, or 5 over 2. And if I plotted 5 over 2, it would work out really nicely, right? It would be the clear answer. And sometimes in math, we just want to take that clear answer. If I were to take the other portion and I set that equal to 0 and I go about solving it, right, and I take the x squared minus 5x plus 9 essentially is what I'm looking to solve. The first thing I would want to do, it's not factorable, but I could do b squared minus 4ac. I could do the discriminant to see if it's even going to give me a real solution. And in this case, 25 minus 4 times 1 times 9 is 36. That is going to give me a negative value. So right away, that is going to be an imaginary solution. Sometimes it comes out imaginary and you're like, okay, obviously that's not the answer. Sometimes it just comes out to be a mess. And you're still saying, well, it's a real number. How do I know? Again, just logic through this one. But there are some other explanations out there that have to do with linearity and such. Okay, so anyways, x equaling 5/2 is the x coordinate. So then the square root of 5/2 is your y coordinate, and that's going to be your answer. Okay. Every time, people. So on the AP, when you see this types of question, take that shortcut. You know, there's not too many shortcuts out there for us, so use this one to your advantage. Okay. All right, and then question 5. So last one for this video. And in question 5, it's a little bit of a challenge because we do have two equations that we're going to have to work with in order to come up with our final answer. So the question reads, the volume of a cylindrical tin can with top and bottom is to be 64 pi cubic inches. If a minimum amount of tin is to be used to construct the can, what must the height be in inches? So we're minimizing the amount of tin. So essentially that's a surface area, right? And we're looking for that height as our answer. We are being given information about our volume though. So that's what we need to use because the surface area formula has R's and has H's in them. If our answer is about a height, we want to make sure that the height remains in our surface area equation and the radius is removed. So I'm taking the volume formula and the information about volume simply to rewrite my surface area. So the volume is pi r squared h, and then 64 pi is the volume. So I set that equal to pi r squared h. The pi's cancel. And then we have 64 equals r squared h. So I want to solve this by dividing by h and then square rooting. So now I have this relationship that r is equal to 8 over root h. Okay. So I'm going to use this and I'm going to put it into my surface area formula. Everywhere there's an r, we put an 8 over root h in there. Okay. Now I clean it up. Before I derive, I clean it up. So I have a 2 pi times a 64, so I have a 128 pi. I have a root h squared, so that becomes an h in the denominator or an h to the negative 1. I have 16 pi, and an h over a root h would be an h to the 1/2 up top. Okay, so much easier now. I just have a power rule to derive. So surface area prime is negative 128 pi h to the negative second plus 8 pi h to the negative 1/2. Okay, awesome. So when I'm deriving, I want everything in the numerator negatives, rational exponents. When I'm solving now, for me, it's easier to think about things as fractions. So I'm going to bump h to the negative second back down, and h to the negative 1/2 down as a square root. But that's just preference. So I have 0 equaling 2 fractions, which is great because I can turn it into a proportion. I can cross multiply. Okay. I can divide by a root h is what I'm going to do first, just to get the h's together. So h squared divided by h to the 1/2 would be a 3/2. Now I can divide by my 8 pi. So 128 divided by 8. It's going to be 16. So h is equal to 16 to the 2/3, or the cubed root of 256. So I'm okay with the answer of 16 to the 2/3. It's also equivalent to 4 cubed root of 4 inches. I'm totally fine with either, but if it were a multiple choice question, 4 cubed root of 4 would be the answer that you'd have to come up with. Okay? All right, so that's your optimization, coming up with the best case scenario for whatever the problem is presenting.